Okay, let's get started. Welcome back. So we're going to finish up 11.8, which is talking about Lagrange multipliers. So let's just kind of do a brief recap of what we were talking about yesterday. So what we were trying to do was find the closest point on the surface that we called this x squared minus c squared minus 1 is equal to 0. And we were trying to find the point on the surface that was closest to the origin. So the idea here was, imagine maybe our surface kind of looks like this when we're viewing it from the side. And we have this steadily increasing sphere that we're trying to get to just touch the edge of this surface. And we're trying to figure out where it hits that surface. So what we did was we constructed a function f, which needs to be equal to a constant. And this is the thing that we're trying to minimize or maximize. So in this case, we're trying to find the minimum distance to this surface. So the thing we're trying to minimize is distance. So what we did was we said that f was x squared plus y squared plus z squared, and this was equal to some constant, the distance squared. Then we also have a constraint function, meaning the thing that always needs to be true. So the point has to be on the surface. So this is our constraint, and we call this function g. And we also want this to be equal to some constant. Well, it's already equal to 0. We could have also moved over this 1, but we'll just kind of write it as is. This x squared minus z squared minus 1 is equal to some constant 0 in this case. So by doing so, what we've done is created our 4 functions that take 3 variables in and output a 4th variable. So these are both in R4, but since they're both equal to a constant, these are the level surfaces that we were talking about, right? These are level surfaces in R4. And the cool part about that was we found the normal line for these things as the gradient of the functions at that location. Well, cool part about this sphere that's steadily getting larger and larger until it hits this point, as soon as it touches this surface, we know that they share a normal plane. And if they share a normal plane, that means that their normal lines are in the same direction. But there might be a factor that just differs their magnitude slightly. So remember, the normal line was the gradient of these guys. So at that point, we know that the normal lines are parallel. And to be parallel means that there is some constant magnitude difference between the two. Maybe it's 1, maybe it's not. But what we've done is just introduce this parameter here, lambda, that make these 2 vectors equivalent. So now that we have our f and g, let's actually go ahead and find the gradient for these 2 functions. So here we have 2x, 2y, and 2z. Then we have lambda times the gradient of g, which is 2x, 0, and negative 2z. Okay, but look at this. This is 3 equations, isn't it? It has their x expressions need to be equal, the y expressions need to be equal, and the z expressions need to be equal. So we can write that down as 3 different things. We have 2x is equal to lambda times 2x. We also have that 2y is equal to lambda times 0. I'll just write that as 0 here. And then we have 2z is equal to negative lambda 2 z. Okay, so now we have 3 unknowns. Well, actually, sorry, we have 4 unknowns because we have x, y, z, and now lambda. But we only have 3 expressions here. So without a 4th equation, we can't solve this. But lucky for us, we have a constraint. It has to be true that our g is satisfied, meaning that this guy right here is our 4th equation. So we'll just throw that in. X squared minus z squared minus 1 is equal to 0. So now these are 4 equations and 4 unknowns. So let's see if we can start to solve this. And of course, kind of like a precursor to kind of doing this, because we're going to be doing this type of scenario a lot where we're solving these systems, there's no one way that's correct. So you could do a multiple different ways to kind of get to the solution. This is just my attempt at doing so. So I'm going to look first at the x expression. So I have 2x is equal to 2 lambda x. This gives us that either lambda is equal to 1 or x is equal to 0. Right? Those are the only 2 instances that this is true for. Right? If lambda is not equal to 1, right, it's equal to something else, then I have 2x is equal to another multiple of x, which can't possibly be true unless x is equal to 0. So I have this either or statement. Okay, so can we rule any of these out immediately? We can. We have to. This is where we have to be really conscious of what we're trying to do here. So this x equals 0 case, what happens if I plug it into our 4th expression here, this constraint function? I get negative z squared minus 1 is equal to 0, right? So if you look at that and you kind of simplify it, this means that z squared is equal to negative 1 if x is equal to 0. I don't want that. We're not dealing with imaginary numbers. We want points in the real space, right? We definitely know that the point closest to the origin is a real number. Can't be this imaginary nonsense. We're not going to talk about imaginary numbers in this class. So lambda equals 1 seems like the only scenario in this case that makes sense. So let's continue from there. If lambda is equal to 1, then I can look at my z expression. So 2z is equal to negative 2z. Okay, the only way that this is true is that z is equal to 0, right? You can even do it algebraically. You can move this over and you get 4z is equal to 0, and then z is equal to 0. Okay, so now that we've got lambda is equal to 1 and z is equal to 0, we're looking good so far. Let's keep going. Did we talk about y? Oh, no, we didn't talk about y. The y expression is just 2y is equal to 0. That had nothing to do with lambda. So we can definitely say that y is equal to 0. So now what I have is that if lambda is equal to 1, I have that z is equal to 0, and I have y is equal to 0. This means our solution is in the form x, 0, 0 so far. Could you solve the 4 equations with a matrix? Yes, but we're not going to talk about that in this class. So if you've taken DiffyQ and you talk about matrices and solving these linear systems, this in fact is a linear system. We could set it up to solve with a matrix. But unfortunately, you can do it. You can do it on your work, or you could do it on an exam if you would like. But for those of you that don't know how to use matrices to solve these problems, don't worry about it. Just do it the way that we're kind of detailing here. But yeah, that's a good question. So this means our solution is of the form x, 0, 0, since we know that y and z is 0. Okay, well, our last constraint, or our last equation, was this x squared minus z squared is equal to 1. Right? I just moved the 1 to the other side. So I go ahead and I look at this as x squared minus 0 squared is equal to 1. This means that x is plus and minus 1. So the points closest to the origin that are on the cylinder are plus and minus 1, 0, 0. And that makes sense because we have a duality in our solution. We have two solutions here because the function, the surface, is actually symmetric across the origin. So it makes sense that our sphere touches these 2 points simultaneously. Okay, now that we've done it for this problem specifically, what is the method of Lagrange multipliers? What did we really do here? So the method of Lagrange multipliers. To find the maximum and minimum values of some function f, x, y, and z subject to the constraint g of x, y, z is equal to some constant k. First thing we'll do is find all values of x, y, z, and lambda such that the gradient of f of x, y, and z is equal to lambda times the gradient of our constraint function g, x, y, and z. And our constraint function is still satisfied. So from before, this was our 4 equations, right? We had the 3 coming from our gradients being parallel, and then we had our 4th expression being this constraint function here. So then, for step B, we evaluate all points x, y, and z from part A the largest / smallest is the max / min. So it's pretty simple, right? These are the 2 steps that we do. But the work really comes from part A here, where we have to solve this system. Taking these derivatives should not be bad. It's just really kind of going through and solving this system here. Okay, so let's do some examples. The cool part about this is that you can generalize it to any dimension too. All right, so our example is find the max / min of the function. Let's start pretty easy. Let's do just x and y. But we're on the ellipse. X squared over 8 plus y squared over 2 is equal to 1. Okay, so we're constrained to the ellipse, and we're trying to find the max and min of our function x, y. So I think one of the first real steps is to kind of figure out, of course, what your f function and what your g function is. Now, I did call this f, so it's a dead giveaway, but maybe a word problem doesn't state that, doesn't say f. It just gives you some thing, right? And you have to figure out what your constraint is versus what it is you're trying to maximize and minimize. So here we're trying to find the max and min of x, y, but our constraint is that we're restricted to this ellipse here. Okay. So we're going to set our constraint function g of x, y equal to x squared over 8 plus y squared over 2 is equal to 1, right? 1's a constant. We can leave it on the right-hand side there. Okay, step A. We're going to take the gradient of f and set it equal to lambda times the gradient of g. So I go ahead and look at my gradient of f. This is just going to be y x, and then I have equal to lambda, and then the gradient of g. I take an x derivative, I get x over 4, and then I take a y derivative, I just get y. So my system to solve is y is equal to lambda over 4 times x. X is equal to lambda times y. And then I have my constraint function here, just x squared over 8 plus y squared over 2 is equal to 1. So now down here, this is not a linear relationship. So for those of you that want to do matrix solutions, you can't do that here. This is no longer linear. All right, so now let's figure out what to do. Actually, even before, when you had our constraint was not linear. So I actually misspoke for the earlier example. Yeah, our constraint wasn't linear, so we couldn't do a matrix solve. But your head was in the right place. You had a system. It just wasn't a linear system. Okay, so now let's plug in x into our second expression here, or sorry, our first expression. So we have that y is equal to lambda over 4 times lambda y. This means that y is equal to lambda squared over 4 times y. So here we have two solutions, and it's really important to keep track of this, like these cases that happen. So either y is equal to 0, or I have that lambda is equal to plus or minus 2. Right? Because if lambda is plus or minus 2, then I'll just get that y is equal to y, and we're good to go. Y could be anything. But if it's not, this coefficient is not 1 right here, then y is certainly equal to 0. Okay. So can we rule any of these out? But we know that if y is equal to 0, we can look back at our first expression here, that if y is equal to 0, sorry, our second expression, we definitely know that x is equal to 0. But the origin isn't on the ellipse. So it fails our third function here, our third equation, right? If we plug in 0, 0, we don't get 1, right? So 0, 0 is not on the ellipse. So that rules out this case. So we can say, nope, it's not y is equal to 0. So let's keep digging. Let's look at this lambda. So now, maybe we can roll out one of these signs, or maybe we can't, but we have to keep going. So lambda is equal to plus or minus 2. We can plug x is equal to, now because x is equal to lambda times y, this means that x is equal to plus or minus 2y into the ellipse. So if I plug that in, I get plus or minus 2y squared over 8 plus y squared over 2 is equal to 1. So I can reduce this. This is 1/2 y squared plus a 1/2 y squared is equal to 1. Or that y squared is equal to 1, which means y is plus or minus 2. Okay, so it's important here when we start using all these plus and minuses to really keep track of what means what. So if lambda is positive 2, right, and I plugged in the positive here, I still got y squared is equal to 1, which means that y is still plus or minus 1, regardless if I chose the positive or negative for lambda, right? Because if I plug in negative 2 for lambda, I still get y squared is equal to 1, which means that y is equal to plus or minus 1. So regardless of the plus and minus that I choose on lambda, I also get a plus and minus on y. So we have to keep that in mind. So then, because x is equal to lambda times y, x is equal to plus or minus 2 times plus or minus 1. So I can have a plus 2 and I can have a plus 1, which will give me a positive 2. I can have a minus 2 times a positive 1 and get a minus 2. Or I could have, any combination. But the end of the day is I still have a plus and minus 2. So what the question to ask ourselves is, how many points do we have now? If I have x as plus or minus 2 and I have y as plus or minus 2, does that mean I have 2 points? Or do I have 4 points? Well, the x did not depend, this plus or minus did not depend solely on the plus and minus of y, right? If, let's say I chose that y was equal to 1, I still have this plus or minus from the lambda, which gives me a plus and minus 2. So y is equal to 1 still gives me x is plus or minus 2. Y equals negative 1 still gives me x is plus or minus 2. So that means that I have 4 points to check. This gives us 4 points. So it's really important to kind of make sure we keep that logic. Minus 2, minus 1. So it's all the combinations of these. Minus 2, 1, 2, negative 1, and 2, 1. So these are the 4 points that are the solutions to our system. So step B, we're going to plug in. So we're going to plug this into our f of x. So our negative 2, 1 gives us a 2. Our negative 2, negative 2, negative 1 gives us 2. Negative 2, 1 gives us negative 2. 2, negative 1 gives us negative 2. And 2, 1 gives us 2. So the max of 2 occurs at negative 2, negative 1, and 2, 1. The min of negative 2 occurs at negative 2, 1, and 2, negative 1. Okay, so let's do another one. Let's do another example. Let's again find the max and min of f of x, which is 3x plus 4y, on the circle x squared plus y squared is equal to 1. So the thing that we're trying to minimize or maximize is this function f here, this 3x plus 4y, and our constraint is that we're bound to the circle x squared plus y squared is equal to 1. So let's set our constraint function as g, which in this case is x squared plus y squared is equal to 1, the constant 1. So then we look at the gradient of f and set it equal to lambda times the gradient of our constraint function g. This gives us 3, 4 is equal to lambda times the vector 2x, 2y. So our three equations are that we have 3 is equal to 2 lambda x. We have that 4 is equal to 2 lambda y. And we have x squared plus y squared is equal to 1. Okay. So let's solve this. Looking at my first expression, I can say that x is equal to 3 over 2 lambda. And I can look at my second equation here and then say that y is equal to 2 over lambda. Okay, so I'm going to plug both of these in to my constraint function to see if I can solve for this lambda. So we're going to plug into x squared plus y squared is equal to 1. This gives me 3 over 2 lambda squared plus 2 over lambda squared is equal to 1. Can simplify a little bit. Let's actually do these squares out. We get 9 over 4 lambda squared plus 4 over lambda squared is equal to 1. So I can multiply both sides of this by 4 lambda squared. And here I get just a 9. Here I get 16. And then I get this is equal to 4 lambda squared. So I get that lambda squared is equal to 25 over 4. Or that lambda is plus or minus 5/2. Okay, so now that lambda is equal to plus or minus 5/2, I can look back at my x expressions, x and y expression. So I have x is equal to 3 over 2 times plus or minus 5/2. And I have that y is equal to 2 over plus or minus 5/2. So this means that x is plus or minus 3/5 and y is plus or minus 4/5. Okay, next question. How many points does this mean that we have? Does this mean that we have 2 points, or does this mean that we have 4 points? So let's kind of keep track of what we're doing with this plus and minus here. And think about it in each case. If lambda is positive, then I plug in the positive version here, and I get the positive version here, which also means that I plug in the positive version here, which means that I get the positive version here. So both of them are positive if lambda is positive. If I plug in the negative, then both of these are negative. So it looks like I only have 2 points, right? I don't have the like the negative here and then the positive here, because they follow from the same case. This is positive if lambda is positive, this is positive if lambda is positive, and vice versa if it's negative. So we only have 2 points in this case. So thus, we need to check the 2 points (3/5, 4/5) and negative 3/5, negative 4/5. So we plug those in. So f at 3/5, 4/5 is equal to 5, and f at negative 3/5, negative 4/5, plug that in, and I get negative 5. So the max of 5 occurs at 3/5, 4/5, and the min of negative 5 occurs at negative 3/5, negative 4/5. Okay, and that's the end of this example. I do want to just talk briefly about if we have a constraint that limits us to a region rather than a curve. So notice here that we were limiting ourselves to the circle or the ellipse. Oh, hang on, we have a question. Could you please explain how we know there's 2 points and not 4? Sure, I think that's an important point. In the example before, let's kind of go all the way back up. In the point up here, we had that lambda was plus or minus 2, right? And that meant that because x is equal to lambda times y, that x is equal to plus or minus 2y. Regardless of what sign I chose, y inherently is still plus or minus 1, right? So if this is confusing, then don't do this plus or minus. Say that x is equal to y. You plug that in, you get y is equal to plus or minus y still. If you plug in negative 2y into this, you still get that y is equal to plus or minus 1. Right? So regardless of which version of the plus or minus you chose here, you still got the plus or minus here. That meant that regardless of x being plus 2 or negative 2, y was still plus or minus 1. So that gives us 4 total combinations. This is opposed to what we did just down here, was that x was reliant on either lambda being positive or negative, right? So if lambda is positive, both x and y are positive. If lambda is negative, then both x and y are negative, right? There's no combination here that means that I get the plus on one and the minus on the other. Another question is, so essentially there are two options for every variable that is plus or minus. You have to be really careful. You have to keep that logic, right? If it's too condensed, this plus or minus form, then break it up into every single case, and you'll certainly get the right number of outcomes, right? So if we had up here, as soon as we got this split, we did the lambda equals 2 case, and then we later did the lambda equals -2 case. If you did that, you would certainly get the 4 points, right? So as soon as we did this down here, if we said, oh, lambda is plus and minus 5/2, you do the lambda equals 5/2 case, and you get that x is the positive, and then you get y is the positive. And then you do lambda is the negative case, and then you get x as the negative and y is the negative. So you would only get the two options. So if you are not confident in keeping track of the plus and minus, do every single case separately, because that's very important. Because what would have happened here is we could have accidentally said this was 4 points when it's really not, and we would have tested those 4 points, and maybe one of those happened to be larger or smaller, but it's not necessarily a local min or a max. So we would get into trouble there. But it happened that even if we did that for this case, these would have still been the absolute max and absolute min. Okay. So what I was saying earlier was, if we have a constraint that limits us to a region rather than a curve, so before we said we were constrained to a surface, or we were restrained to an ellipse or a circle, rather maybe I say what we can do is we're restrained to a region, kind of like how we did in the last section, right? There's some region. What we can do is we can compare the min and max of the interior found by the second derivative test. And then what we could do is min-max of the boundary using Lagrange multipliers. So remember back from last section, we had to test each one of those boundaries for maybe that triangle example. Well, what we could have done, instead of doing it like kind of like the Calc 1 way where we substitute that path in, we could do Lagrange multipliers. So imagine that, let's do kind of a quick sketch here. I'm trying to find the min and max of some function on this domain. I could find when the derivatives are equal to 0 and find all the critical points that are in the interior. And then if I have some function g of x of y that's equal to some k that details the edge, the boundary of this guy, I can use Lagrange multipliers on that to see where the min and maxes are along the boundary, because that's a constraint. And then we could do a comparison of the critical points in the interior as well as the min-max on the boundary. So Lagrange multipliers kind of just take the spot of part B from last section, or step 2, I think we called it. Okay, with that, that ends 11.8. Why don't we take our 5-minute break, and then we're going to talk about Taylor series. So go ahead, get a drink of water, go use the restroom, and we'll be right back. Okay, welcome back. We're going to start talking about Taylor series. And there was a question during our break if Taylor series is on this exam. It is. This exam will include Taylor series. So I've also added a supplement onto Canvas if you would like to check that out, because Taylor series isn't really discussed in your textbook in more than one dimension. So if you want to take a look at that supplement, or you just want to talk about how we do it here, that's perfectly fine. So Taylor series. So we're not going to talk about radius of convergence and all of that. We're just going to see how we derive a Taylor series in more than one dimension. This is not section 11.9. There is, I don't think your book has a section 11.9. I think it ends with 11.8. I might be wrong, but I don't think it talks about Taylor series. Or maybe it does applications or something. Yeah, so this is just in addition. So let's recall for functions of one variable that the linearization was that f of x was approximately f at some point a plus the derivative at a, and then x minus a. So this is what we learned in Calc 1, this linearization. But in Calc 2, we learned that this was the first terms of the Taylor series. Where we said that f of x is equal to the sum from n equals 0 to infinity, the nth derivative at a over n factorial times x minus a to the nth power. I sure hope that looks familiar. So the idea here is, can we write, or can we kind of derive this infinite sum for a function of more than one variable? And we're going to kind of take a different approach to this than in Calc 2. So what we're going to do is, for functions of two variables, so for functions of two variables, we consider the operator that's defined as delta x times partial x plus delta y partial y, where this delta x is x minus a, and delta y is y minus b. All right, so what do I mean by this differential operator? It means that this is something just like a normal derivative, but it gets applied to a function. So what happens here is there's going to be a partial y that acts on a function, and then it gets multiplied by this delta y. it also gets differentiated with respect to x and then gets multiplied by this delta x, and then we add those two things together. So what we do is if we apply this operator once, so we have delta x partial with respect to x plus delta y partial with respect to y, and it acts on a function of x and y. And then what I want to do is once I act on f, I want to evaluate at x, y is equal to a, b. So this is equal to delta x times the x derivative at a and b plus delta y is equal to, times f of y at AB. So what I'm doing is I'm considering delta x and delta y to be constants once I plug this guy in here, right? Otherwise, it would have just been 0. So we don't plug AB into delta x and delta y. We keep them like this until the evaluation is over with. So if I now, after I've substituted in a and b, I put in the definition for delta x and delta y, I get x minus a fx at AB plus y minus b fy at AB. So we've actually seen this term before. And there's a reason that we started with talking about this linearization example, right? In Calc 1, we learned about this linearization. But in Calc 2, we learned that it was the first term in this Taylor series approximation. Well, this is no different. This is part of our linearization. So recall our linearization of the function at AB was that f of x and y is approximately f at AB plus fx at AB times x minus a plus fy at AB y minus b. Right, there it is. This is the term that we just found, applying this differential operator once, right? So you can imagine if I applied this 0 times, I just get f at AB. So we get the 0th order, right? We just apply it no times. We apply it 1 time. So what happens if we keep applying this? What happens if we do this twice? So I have delta x, and I have my x derivative plus delta y derivative, and I means if you square this thing, it means that I am applying this twice. It also means that we can FOIL it out. And we're applying it to some function. And we're evaluating this at the point AB. So now we're still considering delta x and delta y to be constants all the way until the end. So what happens if we apply this twice? Well, think about it. If we square out this differential operator, we get a delta x squared. We get a second derivative with respect to x. And then we get the cross term, which is 2 delta x delta y of partial x partial y. And then we get a delta y squared and a second derivative with respect to y. And this is still acting on our function f, and it gets evaluated at a and b. Okay, so let's go ahead and apply that. I get the second derivative of f at ab times this delta x squared, which is x minus a squared. Then I get plus 2 times f xy or yx, depending on how you orient this term. As long as they're continuous, we can reverse the order. That's why we kind of group these together. At AB, at x minus a and y minus b. And then finally, we have the second derivative with respect to y at AB of y minus b squared. Okay, so this is very, very close to the next term in our Taylor series approximation. This will kind of give us a better approximation if we tack this on. But remember, from the Calc 2, or the function of one variable definition for a Taylor series, we had that factorial, right? Well, in this case, if we divided this thing by 2 factorial, or just 2, we end up with a better approximation. So let's just kind of put that in writing. If we divide this all by 2 factorial, we get the next term in the Taylor series. So this means that the quadratic approximation is then, instead of a linear, we're doing a quadratic now. We're doing a little bit better. This is approximately f at AB plus this operator acting once on f, evaluated at AB, plus 1/2 times this differential operator applied 2 times to f, evaluated at A and B. So let's suppose the function f of x and y has n plus 1 continuous partial derivatives. In an open region D near the point AB. Then we say that f of xy is equal to the sum of I equals 0 to n. Remember, we have n plus 1 continuous partial derivatives. This is 1 over I factorial times this differential operator applied I times to the function f evaluated at AB. Now this is outside of the sum, so we're done with the sum here, plus 1 over n plus 1 factorial the differential operator applied n plus 1 times to f evaluated at C1 and C2. So you might seem like this is kind of reminiscent of our Taylor series in its remainder form, right? If we have an infinite number of continuous partial derivatives, so you can keep taking derivatives and they're still continuous, then this just becomes an infinite sum, right? And then our function is certainly equal to this infinite sum, and we got our Taylor series. If it's not, if we have n plus 1 continuous partial derivatives, we have to stop. We can't keep applying this over and over again. So then that means that this thing down here ends up being the remainder term. And that should kind of ring some bells back from Calc 2. Okay. Where the remainder term is evaluated at some point on the line connecting the point AB to the point XY. So if you have X and Y here, we've got some line segment. Well, this is the point AB. And this is the point that we're trying to evaluate, x and y. Well, here, this distance on the x-axis is delta x, and this distance on the y-axis, kind of, should have drawn this a little bit higher. Right there. That's delta y. And the point that we're evaluating, this remainder term is, at C1, C2, is just somewhere on that line. And that's exactly how the remainder term worked with functions of one variable. It's just that, on a line, you just have an interval, right? But now this line could be in R2. Now, you never found that evaluation point in Calc 2. You're not going to do it here. There's no way that we're going to find what C1 and C2 are. But we are going to use the remainder term, just like we've done in Calc 2, to come up with a error bound for our approximation when we truncate this Taylor series. So if we stop somewhere at maybe n equals 5, the next term will provide a estimation for the error, the upper bound of the error that we could possibly expect when using that approximation. Okay, so let's do an example. Let's find a quadratic approximation to the function of x and y, which is sine of x times sine of y near the origin. So near the origin implies that our Taylor series is centered there at the origin. So we're going to try to come up with a quadratic approximation. So it should have all powers of x and y that go up to the quadratic terms. So for that, we need f, fy, fx, fyy, fyx, and fxx, all at 0, 0. So let's go ahead and calculate these derivatives first. So we need fx, which is just going to be cosine of x times sine of y. The first derivative with respect to y is then sine of x cosine of y. If I take two derivatives with respect to x, I get negative sine of x sine of y. If I look at their mixed derivative, so I take an x derivative and a y derivative, or vice versa, these are continuous functions, they're derivatives, so we can swap the order. So we can do cosine of x cosine of y. And then if we do two derivatives with respect to y, we get negative sine of x sine of y. Okay, but we still need all of these things evaluated at 0, 0. So let's go ahead and actually do f of 0, 0 here at the top of the list. We go ahead and plug that in. Well, if we plug in 0, 0, here we get 0. Now fx at 0, 0, we plug in 0, 0, we get 0. If we look at fy at 0, 0, plug that in, we also get 0. We look at fxx at 0, 0, lo and behold, we still get 0. If we plug f, or the origin 0, 0, into f of xy, we don't get 0, we get 1. And then finally, if we plug in 0, 0 into our second derivative with respect to y, you guessed it, we still get 0. So there only looks like there's one non-zero term, this mixed term, f xy. Okay. So then, sine of x sine of y is approximately f0, 0, which was 0, plus the x derivative at 0, 0, which was 0, times x minus 0, plus fy at 0, which was 0, times y minus 0, plus 1/2, and then we have fxx, which was 0, times x minus 0, plus, we can't forget that there's a 2 on this term. There's a 2 times fxy at 0, 0, which is just a 1. And then x minus 0, oh, sorry, this should be squared here. It's x minus 0 squared. And then this should be x minus 0, and then y minus 0. And then we have the last term, which is fyy, which is 0, times y minus 0 squared. So a lot of zeros, but it's nice to plug it into the form for the first time here. Right? If you look back at our quadratic approximation, this is just us plugging in everything we've got. So this right-hand side is equal to everything is 0 except for this little grouping in here. This is 1/2 times 2 times 1, so it's just times 1 of x times y. So that was a lot of work for this little x times y. So now this is the quadratic approximation for this function because it's all of the powers up to the quadratic terms, right? This is a quadratic term because it's an x times a y. Now, it's funny because we should have actually kind of expected this. Why? Because think about sine of x on its own. If you wanted to know the approximation of sine of x for very small angles, I have a question here. Don't we have to divide by 2? You do, but there's a 2 out in front, so they cancel. So if you have a small angle for x, if you have a small angle for sine of x, then you have a that small angle approximation is just x. If you have a small angle approximation for y, that's just y. So this is the small angle approximation. A follow-up question, I meant 2 factorial. Well, 2 factorial is 2. And that's what this 2 is right here. Okay. So let's talk about how to kind of memorize the coefficients that are out in front. So you've kind of seen that if I apply this operator a number of times, I get this, this coefficient of 1, I get a coefficient of 2, and then I get a coefficient of 1 again. So let's kind of talk about that and how to do it for ourselves fairly quickly. For n that's greater than or equal to 3, the term might be hard to think about without writing everything down. Right? How does this FOIL when I have a power 3 here instead of a power 2 term? Right? Where if I have 4, 5, 6. So what we could do, and you could do this for, you know, an a plus b to the nth power. Right? It doesn't necessarily have to be this differential operator, but here we have it, this differential operator. We can use the binomial theorem or Pascal's triangle. I like this option a lot more. So what is Pascal's triangle? If you haven't seen it before, what you do is you start off with a 1, followed by on the next row, a 1 and a 1. So this gets us started. From then on out, what we do is we write a new number in between the numbers that exist, where the edges are always 1. But anywhere in the interior, what we do is we add the things above it. So 1 plus 1 is 2. And then at the end, again, I have 1. So this is my third row. I go again, I have 1, always start off with a 1, but then I have a 1 plus a 2. So I get a 3 here. Then I get a 2 plus a 1, which is a 3, followed by a 1. All right, so that's our next row. The one after that always starts with a 1. Then we get 1 plus 3, which is 4. And then I get 3 plus 3, which is 6. Then I get a 4 and a 1. And we'll do one last row just for kicks. We'll do 1, 5. That should just be a 10. A 10, a 5, and a 1. These are the coefficients that show up. So when you FOIL, if you have a plus b squared, you get an a squared plus a 2 times ab plus a b squared, 1, 2, 1. Those are the coefficients that line up. If you have an a plus a b cubed, you go down to the next row. This is an a cubed plus 3 times a squared times b plus 3 a b squared plus b cubed. So it always goes in that order when you're kind of just dropping down in orders of a, or you're going up in powers of b in the other direction. Do we do an example where we apply this triangle? You mean like right now? Or so we're using this triangle because this differential operator is this nth power. So we need those coefficients, right? So if you go all the way back up, right, when we applied this term twice, when we FOILed it out, we got a 1, 2, 1. But if I wanted to do the third term, I would have to kind of memorize what those coefficients are, which I now know because of Pascal's triangle is 1, 3, 3, 1. So this just helps us memorize those coefficients that you have to include. It's not all just ones when you do that foiling out. So I guess let's do the third guy there. So let's say I wanted to do we're applying our differential operator and we're applying it 3 times to the function at AB. So notice I don't have the 1 over factorial out in front. I'm just doing this guy. So you would have to divide by a 1 over 3 factorial, which would just be dividing by 6. But if I want to know what this guy is here, hang on, we're getting a lot of questions. Let me finish this and then I'll talk about some of these questions. So if I want to FOIL this guy out and I have cubed, I can read off the coefficients for my Pascal's triangle. So it's my first guy cubed, right? So I have delta x cubed, and then I have the third derivative. Oh, that's the second. The third derivative, or I should just do it like this. So this is f x x x, right? The third derivative at AB. Then I go down 1 in x, but remember my coefficient here is 3. So 3 delta x squared delta y f x x y at AB. Then I go down in a power in x and up in a power in y. And my coefficient is 3 here. So I get 3 delta x delta y squared f x y y at AB. And then finally, I don't have any x's, I have 3 y's. And my coefficient here from Pascal's triangle tells me it's a 1. So this is delta y cubed f y y y at AB. So that's that third derivative, or applying this differential operator 3 times. So that's why we kind of went over Pascal's triangles, to remember what these coefficients would be, just offhand, right? And if you would do the fourth iteration of this, so you apply this 4 times, your coefficients will be 1, 4, 6, 4, 1, as you go across and drop down in powers of x and go up in powers of y. Okay, so yes, so on the exam, you're going to be asked to do Taylor approximations as well as error approximations, which we haven't talked about just yet. So we're gonna probably finish up maybe the first like 10 or so minutes of tomorrow talking about this error approximation, maybe a little bit longer, because we have to talk about how to do it, and then we'll do some examples, and then we're going to move on to starting chapter 12. So yeah, the exam will cover taking Taylor series approximations as well as error bounds. So if I ask for, say, the cubic approximation of a function, you need to do this quadratic that we've done above, which includes all of the quadratic terms, right? as well as applying it 3 times here to get the cubic terms. So that's why we kind of went over this, because we need these coefficients, 1, 3, 3, 1. Okay, with about 5 minutes left, I don't want to get started with the error approximations, so that tomorrow we can just right off the bat start with these error approximations, and then we can dive into chapter 12 once we're done with that. Okay, so I'll stick around for another 5 minutes to answer any questions that you guys have. Otherwise, stay safe, and I'll see you tomorrow.